Why, hello there, and welcome to Chapter 10. Chapter 10 is Heteroscedasticity. Yes, I said that right. Heteroscedasticity. Right? There was actually a journal article once that asked the question, should it be spelled heteroscedasticity or heteroscedasticity? And you'll see the critical difference here being the C here versus the K there. And so when I went to school, I believe my professor spelled it with a C. I don't remember now. But there was actually a published academic paper once that looked at the root of the word and said that the root is Greek. Therefore, it should be a K and not a C. And I'm pleased to say that our author follows that convention. Now, this one's a bit like serial correlation, but for cross-sectional studies. This is not where, now of course, you're not going to have a natural order to the error terms with a cross-sectional regression. So, the problem here becomes this. I'm going to write the letter Z there and explain that in a minute. All right, here's your error terms. In this instance, they are related because of some proportionality factor called Z. It's going to take a minute to get around to what that means. But scedasticity is the variance of the error term. I'm going to cheat here and do the outside range. So that's homoscedastic, all right, the error terms. The range of the error terms is the same everywhere, all right, so it's homoscedastic. And that's important for some of the statistical inferences we make because, I mean, as you can imagine, if the range of variation was like, yeah, it's so-and-so on average, but it varies. Okay, how much does it vary? Well, sometimes, you know, in this case here, well, it's not all the time. So like, okay, well, if I know how much it varies all the time and I know the mean, then I can make some statistical inferences from that information. But what if instead it looks like this? All right, so I got all these purple dots here over a much wider range that as this Z factor, and I'll explain what that could be in a minute. As this Z factor gets larger, for example, or gets smaller, it doesn't matter, we could do it the other way. And actually the variance gets bigger. So you're like, okay, well, I'm trying to draw some inferences about the way that this relationship works. I know the mean. I know that on average it hits right there, but how much it's off the average changes dramatically as this proportionality factor changes. For example, what if we're looking at, I don't know, let's see here. I think I used city, what do you call it, tax revenues, all right, city tax revenues. Let's say you built a regression to show different cities in the United States, their tax revenue, all right? Well, obviously, it's not going to be exactly right? I mean, there's going to be error terms. There's going to be unexplained random variation. But the absolute value of the unexplained variation is going to be a heck of a lot smaller for Waxahachie, Texas than it is for New York City. For New York City, it could be quite a bit off, and we're talking about big numbers to start with for tax revenue for New York City as opposed to Waxahachie. So for very small cities in the United States, the amount that your regression line is off, the stochastic error term, may be way down here, whereas for Los Angeles and Chicago and New York, it may be way over here, all right? So that's the problem, that it is difficult to draw the statistical inferences when the statistical inference changes by which city we're talking about. It's like, well, it's supposed to be homoscedastic. We're supposed to be able to say it's this on average, and it's off sometimes, all right? Well, I shouldn't say sometimes. Roughly speaking, it's going to be in that range. Well, roughly speaking, what do you mean by that? Well, plus this much minus this much. oh, okay, so I can draw some inferences from that. But if it's plus this much or minus this much back here, but different over here, but different over here, it screws up all the statistical tables, right? We need a homoscedastic. Okay, so let's see here, classical assumptions, like and this z factor, he takes a while to get around to this in the book, but let me mention this right now. The z factor is usually one of your variables in your regression, but it doesn't have to be. All right? I mean, you may not have city size in your regression analysis at all, and yet it is a very important factor. It is a proportionality factor because it's determining the proportionality of the variance of the error terms. All right, let's see. I already told you that. Yep. I'm not going to show you this part here. That's easy enough. Oh, I have a confession to make. I don't really care that much about heteroscedasticity. All the research I do is time series, and it's just not as interesting to me. This previous chapter, the serial correlation, I had to deal with that stuff all the time, but not so much this. So I'm gonna give you some basic ideas, but I'm not going to beat this one into the ground. So they make complex forms. Z is called the proportionality factor. I already told you that. Okay. And I kind of like this diagram here. This was showing the, I'm trying to think of an intuitive way to explain this. Do you remember this idea here? Sampling, distribution of, of beta hat. All right, there's the true beta right over here. And when your particular technique does an estimate of beta hat, hopefully on average, if it's unbiased, if on average it gets the right one. But obviously it's going to be off some, all right? It's not going to be exactly there. But you like to have a very narrow variance here. You don't want this. With the purple one, you can be way off of the actual beta, as opposed to, say, this green one, which is very narrow. No, you're not going to get exactly the right beta every time, but you're not going to be that far off either. So that's the sampling distribution. Now, what happens with heteroscedasticity is that the sampling distribution is different depending on where you are. And he's drawn a nice little sort of 3D diagram here in the book. This is 10.2, homoscedastic error term with respect to Z. Notice that let's take the blue one, for example. It's the blue one everywhere. All right, all of those are exactly the same size. Doesn't matter how big Z is, and let's stick with that city size example. Doesn't matter how big it is, you still get pretty much the same sampling distribution. Whereas with this one here, it varies by the size of the city. With a small city, you get that really tall one. It's not going to be that far off, because it can't be that far off because the numbers are small to start with. And then for New York City and Los Angeles, it's that last one on the far right there, where it's that really flat one, like that purple one. So that's a problem, okay? Now, the question is, how do you, and that's the problem. Now, there are two possible reasons for it. One is, just like with serial correlation, impure heteroscedasticity. It could be you just left a variable out, all right? You left a variable out that would have taken into account the size of the city, and it would have pulled that problem out of the thing entirely. So, very first question always is, oh no, I got heteroscedasticity, but did I specify it properly, all right? Now, if you haven't, then you re-specify it. But if you have, now we've got to go on to, okay, well now I got pure heteroscedasticity, and it does not, very similar to serial correlation, it does not cause bias in the coefficient estimates, and it ends up causing the hypothesis testing to be unreliable, right? Now, there are many tests for heteroscedasticity. In the book, he does the Broich-Pagan test and the White test, all right? Well, I don't know why I'm showing you my notes there, I put the notes in here for both of them. Basically, let me just give you a basic idea of what you do. You're trying to check the size of the residuals relative to that proportionality factor. I mean, think about it. What you're trying to figure out is, and you got to come up with a proportionality factor. That's up to you. It's really hard. Again, this is where you reference the earlier literature to make sure that you know what others have done. But you're checking to see, am I getting a wider variation over here? And then similar to what I showed you in the last chapter, where you could put the row in the regression and get rid of, with the generalized least squares, get rid of the serial correlation, you can do something similar here. Remedies for heteroscedasticity. If it's found, first make sure there's no specification errors. Then you can use heteroscedasticity corrected standard errors, which are designed specifically to avoid the consequences, or you can redefine the variables. You could do per capita or tax revenues divided by the overall income being generated in that city. So now it's already taken into account. That's all I really got to say. As I say, I've never found it real interesting. I don't run into the problems myself. I do time series stuff. I want you to have a basic idea about it. I've got a few simple homework questions on it, but I don't have any strong desire to go through the Broish-Pagan or White test with you, and I suspect you feel the same way, especially because this is where I used to stop the class right here, at this point right here, and I go into more detail on both of those. But I really want to cover a couple of concepts that are relatively new and that I hadn't been covering in class before. This one's not relatively new, but I already told you about the stationarity and the non-stationarity. And then I'm really interested in covering Chapter 16. So in our allocation of our scarce resource of time, I have decided to not do as much on Chapter 10, but let's do Chapter 16. Thank you.